here at ExoMindset. And I've been involved in the computer vision and image understanding from like 20 years. I started studying the University of Stuttgart, image processing and different techniques. And I also published 2 books on the subject of machine learning. In the last years, we have been developing many different computer vision projects, especially with published papers in the area of assistive technologies. So yeah, I will try to bring you a little bit of the awesome field of computer vision and how fun it is to work on this field without being too technical. And I hope you have a better idea of how the field is evolving every time, every continuously, starting from the basics. So let's start from the very beginning. The human eye, which is a marvelous creation, you know. This is the starting point of our discipline, and as you already know, the main parts of the eye are a lens and a surface where the light is received and communicated to the vision nerves, the optic nerves, directly to the brain. So we have the lens and receptive fields and communication ways. And as you might remember from the biology classes, the retina, which is the most important part of this system, has different kind of cells receiving different kind of wavelengths or information, the router cones and other uh, type of cells. So in order to emulate that behavior, we have developed machines working with the same principles. We have a lens and we have different receiving fields for the basic colors. We have red, green, and blue receivers, just like the human vision. And this is the origin of the all the data we are processing and showing in this discipline. So after introducing the mapping from the natural world to the digital world, let's start from the building block, which is the pixel. A pixel is just one of the elements of this discretization of the vision field, because we don't have continuous models. We divide an image into a matrix of values. In the case of grayscale images, we just have a matrix to the structure holding how obscure or clear is any of the pixels. And of course, as you know, this is a zoomed out surface of a TV screen. In order to reconstruct all the colors, we have, for each pixel, we have one data element describing how red, green, and blue is this little discretization of the space. Okay, let's start with the more fun part, which is applying processing to the images in order to get insights. What are the most basic image processing techniques we can have? Okay, in order to get features from an image, one of the first measures we take is to apply kernel operation. What is a kernel? A kernel is a little tiny matrix which contains different coefficients. The effect it has over the image is that we multiply or divide. We can do many different operations over a tiny fraction of the image, and depending on the parameters we have in this kernel, the image will be highlighted looking for different parts. For example, if we use this kind of parameters, the Sobel or horizontal kernel, we will get horizontal oriented borders. Imagine you want to get vertical edges or borders, you use this one, which is oriented at a vertical orientation. We also can do blurring and different other processing just using this 3x3 matrix. So it's a very powerful technique. Related to this operation, we also have morphing operation, morphological operations, which are very similar, but they instead of applying this matrix, they have operations like searching for the maximum value in a vicinity or the minimum, and using that you can delete or include or improve the appearance of the data you want to analyze. For example, this is a graphical representation of how it works. So in this case, as you can see, we have images which have holes in the middle, and depending on the analysis you want to apply, you want to close the little holes in the sample. For example, when analyzing a cell. So what you do is okay, you apply this little matrix over the pixels, and you get the maximum value in the vicinity. So as you can see, for this little hole, it will be closed after the kernel passes over it. So this is a very simple operation, but I will show you shortly how it is very useful for disciplines like life science. Let me go. This is another example we are working on our lab. For example, here we want to analyze peanut seeds, and with this little mask, we want to just work over the peanut surface and not the background. So we apply one operation called binarization. But as you can see, we have lots of garbage over in the intermediate side. So for this reason, this is the main grounding for using this kind of techniques. Here I will show you an example with these are tissue cells that we have to analyze. The goal of this operation is to have them separated and count them to see how many blobs there are on the sample. So the first operation we perform is the binarization. So we convert the areas into black and white, no intermediate representation. Whatever is lower than a threshold, it will be black or white. So this is a first operation. As you can see, if you change the threshold, the areas which will be apparent will change. So you have to search for a very optimum level of threshold for the binarizing to be successful. There are more advanced techniques, but the very original way of performing this is just if the image level is greater than the threshold, black or white in the other hand. Okay, let's continue. We apply the binarization. After that, we invert the mask. So we get the blobs in white and the background in black. So this is very useful for the following analysis. Then I will show you how the convolution operations that we saw before modify the image. For example, they can be used, for example, to detect the edge or sharpen or blurring the images. In this case, this is not very useful. This is not the technique we normally use. I will show you in a few minutes what the most important operation that we perform, but this is just to show you different edge detection techniques that, as you can see, they are not very efficient in order to get this garbage over the surface. But you'll be surprised how well the morphological operation works. For example, here we are applying the erosion operation. So erosion tries to take bits from the borders or of any blob, and it doesn't matter how big it is, it works over the surface. So as you can see, it's been reduced, but in some case it's so aggressive that we are just ending up deleting useful samples. Then I will show you dilation. Dilation tries to grow all the samples, and as you can see, it can be useful to make more clear. The blobs can be made more clear, but as you can see, it also affects the garbage around them. So in that case, this isn't useful. We have another one, which is opening. This is a very useful operation, and it's basically applying erosion and then dilation. So what happened down here? We have just deleted the tiny speckles, and after we apply opening, the blobs are not reduced in size. They return to the original size. So this is a very useful technique, and according to the parameters, we can delete more or less speckles and respect the blobs. And we have the closing operation. Closing operation is like a bridging operation. It detects blobs and tries to join them into one particular entity. As you can see, if we use it used to match, it end up just joining the blobs, and this is a mess. So in this case, my winner, I don't know about you, the opening technique was the winner, and look how clean the blobs are detected and how efficiently the garbage was deleted. So this is a little first step in the way of computer vision. I'm open to questions right now because I'm going to pass to another part of the discipline. Any of you have any questions? Okay. So far, so good.
Yeah.
Okay. Yes. Okay. Now that we have studied or seen the most basic principles of computer vision, we'll give a very long jump in the discipline because there are intermediate steps between the basic operations we have and the neural image understanding, but in order, it is impossible to give everything in one talk. So I'll just jump to the most recent developments and the most relevant ones. So let's start with the neural networks and what they mean in the field of computer vision. As you can maybe have studied or seen everywhere, a neural network is like a mathematical model trying to emulate how the neurons connect in the human brain. We start with the biological original sample of a neuron and trying to emulate how they have weights to communicate through the dendrites with the other neurons, and it has one definite output which is then connected to other neurons. So for this reason, we also have our computational neurons, which are connected with other neurons, and they have an output layer which gives us probabilities about a task we have trained the neural network on. In this case, this is a dog or cat neural network. You maybe laugh at this, but I can assure you that in 2013, 14, creating a neural network able to discern a dog for a cat was like a hit. When it appeared, it was like a blast for everyone. Of course, now it's a matter of laugh about that, but believe me, it was a really significant step. Maybe I think it was 2010, 11, not 15, but you get the idea. So what do we do with this? We present the neural network with the trained neural network with the image transformed into a linear array. And after computing all the original data, multiplying by all the weights and different operations, we only have two different options with a coefficient indicating, okay, this is the probability of it being a dog and a cat. By the way, all the classes normally have some kind of probability. It's very difficult to have a 1.0 probability, and if that's the case, probably the neural network wasn't very well trained. So remember, this is all probabilities, and we are talking probabilities over here, and never get the 100% for almost anything. Well, what's the next step? The convolutional neural networks. These are your natural neural networks, but instead of analyzing the data in a linear fashion, it has like different two-dimension arrays. So if I have to define it in one way, with the convolutional neural networks, we scan the image, the surface of the images with different filters and look for patterns. For example, what does a llama, or sorry if it's not a llama, I don't know the species, but what does this animal, the class it belongs to? Okay, it has two eyes, so probably it's not a car, it's not a stair, you know, it has little ears in this form. So all this information is encoded over these filters. And these filters are trained using thousands or millions of images. So when you present the model with a different image it hasn't seen, it will detect it. And the operation is very similar to what we saw here, you know? The same convolution idea, but in this case, we don't use fixed number. We trained those numbers. So it's much more finer details are detected. And what do we do between layers? We have layers that reduce the size of the images by a half, for example. So if we apply filters on a reduced version of the image, what we get is that the features we are getting are more general. For example, in this big layer, we can observe the very fine details of the eyes, but we also have to consider the global head and the neck and all the parts as structures. So for this reason, we reduce the image size in the last layers. And so in this layer, for example, in some sense, we connect the neck with the head and with the other part of the body to get the final results. Over here, we analyze like the form of the eyes or the form of the ears. In summary, we get a multi-scale image analyzer trained with real data. And here I have prepared another example this is one of the first convolutional neural networks that was released. It was released by the Nobel Prize Yann LeCun. The author of this won a Nobel Prize, so his work was very fundamental. Remember, this was done in 1989, so quite impressive for that year. So this neural network receives, it was created to analyze handwritten checks in order to automatically detect the sums and to do OCR. In this case, for example, I draw a 3, and what happens is that this is the first layer. Then we are training, this is the response of the intermediate layers for that input. Every one of these little features tries to look for something different. For example, the 7 has a little stick for some manuscript styles. So for example, probably one of these filters will look for the medium stick of the 7. So it will improve the probabilities of the final answer to be 7. And so on and so on. And then we have 2 linear layers of the final. As you can see, we have 0, 1, 2, 3. The 3 answer got very enlightened because this is a very clear and definitive answer. So all the other options are, the probabilities are really low, and the only one is 3. So this is working right now. So I started to play a little bit with the inputs to see if I can confound the detector. 2 is perfect. Then, okay, let's calibrate the outputs again. For example, 5, okay, no problem, it detected it well. And now I started to play, okay, what happens if I draw a little 4 and 5? Okay, it didn't get confused, but did you see that when I added the little stick on the upper side of the 5, the number 4, oh, sorry, the number 4 got a little bit of probability because it was like a mix between a 5 and a 4. You see, when I put the little stick on the 5, the 4 got much darker. Well, not much darker, but you see the reduction in light. Okay, so I started to do a mess, and you can see how the model starts to wonder what is this guy doing. So this is a very nice. For example, this is a mix of a 3 and a 2, and I try to convert it into a 4, but it mixes 7 and 4, and okay, it's really funny, and you can see this is a probabilistic model. It can get confused, and it has its limitations. It's not always perfect. Okay, what are the main tasks that we are normally approaching with convolutional neural networks? Well, we have, for example, semantic segmentation. In this case, we want to get the areas of the image and see which class does every pixel belong to. For example, we segment grass, cat, tree, sky. And in the case of object detection, we just need a bounding box. So we need 2 points, the 2 corners of a rectangle, and this will define where the class we are looking for is located. Then we have object detection and classification and localization is more or less the same. And then we have one step forward, which is instance segmentation. In this case, we not only detect if this pixel corresponds to a cat, it also can divide the entities into separate beings. So we can detect this dog from this dog and this cat. It's much more useful in order to do analysis, not just to know this surface is a dog. If it's much better if I can divide the entities into separate beings. And I have prepared another demo because I know you guys like the seeing the things in action. This is a video of fencing, and I prepared an application which applies different kind of convolutional neural network processing. Okay, I start with anything, and over here I applied a YOLO model, which is a convolutional neural network for real-time processing. And as you can see, here we are detecting the two persons with different probabilities, and see how important it is, because we have 78% of certainty this is a person. And you will see, but it's really clear to me, okay, but this model has to detect 90 different classes, so it gets a little bit confused. And I also using a real-time model, so the performance is not so good, but it is working. We normally use more than 50% probability is okay for this kind of analysis. Okay, let me go back. Well, after this, I will apply the segmentation. You can see the image resolution got downgraded because in order to get this to real time, we reduced the resolution to 2024 by 2024. But as you can see, the segmentation model is able to segment the two human beings. But as this is a very limited resources model, it got a little bit confused in some areas. So this is just to have an idea where the person is located. It's better than the bounding boxes, but you get a very low resolution. And then this is the cooler one. This is a key point detection. So we have a model which is trained into the very different limbs and parts of the human body, and then it detects it all at the same time, and then it looks for the different relationships, spatial relationship, because of course there are some structure in the human body, and after that it detects all the main parts of the human body. And so this is one of the many examples of where convolutional neural networks are applied, and there's many different cool samples we could show you, but I think this is enough for this talk. Okay, transformers. Transformers is a very revolutionary technology appearing in 2017, which gives another step in the way of understanding reality and images. If we really simplify the idea, transformer is a way to allow me this little repetition. It transforms from one way of representing reality to another. I won't be digging deeper because this is not a very technical talk, but basically a transformer has an encoder and a decoder. For example, if I have a Chinese text, it tries to encode this kind of no, this is not Chinese, probably Korean, sorry, and it tries to, or Japanese, I'm sorry, I'm not sure about it. It tries to transform from this way of representing reality in a sequence, because the data must be coming into a sequence, into a sequence that is optimized to a goal. In this case, we train this transformer to be a translator, so it gets the original text and it translates it into English. But the amount of tasks that we can do with this is surreal. For example, we can encode music and get music in pop style and get it into a classical style or Baroque style. There are many possibilities for it. And in order to get deeper into the different components of a transformer architecture, we have to understand what is a token. What's a token? A token is a word, is a sign, what it is. It's neither of that. A token, you can visualize it, but it is not 100% accurate, but you can visualize it at it's the atoms, and the words and signs are the molecules. So in order to be able to form the most information with the least amount of tokens, we don't have one token for word. For example, we can have the root token is a token, and isation is another token. So we can form many different words ending with isation. And the same case for everything. So what's a token? It's a minimum a structural element in which we show the information to the model, but it is neither a word, a sign, it's a mix of them. For example, two points, one after the other is a token, and so on. Okay, so we have seen what's a transformer and it's a token. It's time to get to the more recent developments. As you can see, ChatGPT, Claude, we have many different large language models. What are the main features of large language models? The large language models only have a decoder. Then they don't have an encoder. Why is that? First, they have an encoder, but because we normally enter some English words and we get English words at the output, the encoder doesn't have too much sense because the mapping is really direct. And additionally, if we can have models like ChatGPT, we need to avoid having the most structural elements, as many as we can. So yeah, it's more like a practical approach to only have an encoder. So these are the main reasons that we have, that we just want to reproduce from English or computer words into an English or computer words. This is not Chinese to another alphabet. So we simplify everything in order to get performance, because these models consume a huge amount of CPU. It's really we really need to get to a minimum, and additionally it scales better. So this is the reasoning behind we will only study the encoder part. Just as a side note, there are LLMs which have the encoder, but let's get to the most common ones so we get the main idea. Okay, how do LLMs work? Part one. The first part of the LLM is to get the tokens. In this case, this is Hello World, and they have like a map of how every token in the vocabulary, because we have a limited vocabulary, we don't have infinite tokens, how every part of the tokens is related with itself, with the others, and they tend to group into different clusters into the embedding. So, for example, if you have negative sentiments, you have poor and bad usually get together, and then you have good, best, excellent, light. Every bright concept gets grouped together. In the reality, this is not a two-dimensional map. It has like many. So we can't visualize this mapping. So in this very high dimensional space, you can group very complex concepts together. So we get the word world, we map it into here, and then we get the coordinates of it and translate it into a number, which is this is called embedding. And also we need to encode the position of this token into the sequence. So we add just the number or the place of that word on the sequence. Okay, this is the first part. So that's like a tiny encoder part that the LLMs have. In some sense, it's not a complete encoder. Well, this is getting complicated. Bear with me. I will try to to show you what's happening here. Well, the embeddings that we get in this stage, they are mapped into three different arrays. The name is Q, Kate, and B. Okay, what do we store in Q for each token or word we have? I will use the term word and token so you can understand. We in this part we have like a query. We try to identify what kind of information I want from the other tokens or words in my original prompt. Then we have the keys. They are like tags that add information to the tokens in order to help the model to answer. And here is where the magic happens. You know that transformers have a way of working called attention. Attention is the ability to pay attention to certain parts of a sequence and not to others. This is a very different concept like the convolutional neural networks that we saw. Remember over here, these kind of filters, once you train the model, they are exactly the same. What do we do with the transformer? For every part of the image of original image, we pay attention and learn to pay attention to the parts of the information which gives us the best results and insights in order to continue. So this is the most important advantage is the ability to pay attention to the information that matters, and after that combining it and generating an output. Okay, this is a very high level description of how it works, but if you have to live with an idea, LLMs and the transformers in general try to, for each part of the information, pay attention to the most important results, the most important input information, and get a final result. They have the ability to pay attention to the whole sequence in order to get the results. They are not rigid. The only problem of that is that it gets very heavy to the processing part. But over the time, there were many different advances allowing this kind of very complex structures to run in fast. And of course, the beast that the current GPUs are, they are allowing to improve this quite a lot. Okay, I will finalize this little introduction to LLMs showing a real LLM. You can see this is a very complex, and I'm not showing the whole infrastructure. For example, for this head, one of the most, the tiniest model, it has 12 of these attention heads. And then it has many layers of abstractions. So you can really grasp like a little bit of all the concepts. But the main part is, this is the data entering the LLM. And over here, remember I mentioned Q, key, and B. What is this matrix? This is the attention matrix. The most, the bluer one of the elements gets is the most attention the model is paying to that word. So, for example, in this case, we start saying data visualization empower users to. After this whole project, process, what's the output? One word at a time. So the model, every word that ChatGPT is giving to you, it will have a very long list of possible words to continue. You remember the word chain game that you played with the brothers or sisters, that you start with a word and the other continues and you form complete sentences. It's a little bit like that, but the model has a perfect memory. So it isn't too complicated in that part, but it generates like a very complex outputs. And useful outputs. That's the differentiator with a simple game. And returning to the concept, we have an original word, and it has many different possible options. When you play with the model parameters, you are affecting which word it will choose. For example, if you use a temper tag, which is this is a parameter of the model, if you use 0, it just will choose the most probable word. So data visualization empower users to visualize. In this case, it didn't choose visualize. It did choose create. Z, make, easily, quickly. They are all feasible solutions. So you can allow the model to have creativity or not, depending on your needs. Let me check the hour. Okay, 10 minutes to the hour. I will be a little bit faster. Any questions so far? Okay, I hope the cause is that you understood everything, or you didn't understand anything. I can't have any feedback right now. So why was all this information presented to you if this is not computer vision itself? Well, because we have vision language models right now. So with the same principles of the ChatGPT and other models, we can build useful computer vision solutions. So how do we get to having images representations instead of words? Well, the most useful technique or most common technique is, first I divide the original images into little sub-matrices. Then I present them in a linear fashion, and I use a function to convert them into a linear tokens. And as you can remember, I must add the location information in the image. So where every little patch is located into the image. So they took the easiest path. The easiest path. They just transform the every image patch into a linear token. So in the end, there are no difference. This is practically the same model. They used the text tokens in order to introduce the instructions, and the image tokens are practically the same format and everything as the text one. And then we train a large language model with that. So they didn't, they took the same way for that. Well, so in order to show you the new capabilities brought by this architecture, this new transformers-based architecture, this is a software I coded yesterday. It will use a model called Moondream, which is a model able to answer questions, but the output can also be points in the image, captions, or bounding boxes. It is a very flexible model, so it will help us to solve many different tasks with the same model. And I wanted to show you how this new kind of model goes from pixels to perception. Just look by yourself the abstraction of concepts that this model is getting. So this is an image of a group of people, very sad people, and I put, this is generated by AI, a very happy person among them. So I will ask the model to show me the location of happy people. How do you define happy people with a convolutional neural network? It is impossible, or probably the only thing you will have the model to do is detecting smiles or so on. But in this case, you will see that it detects happy people, these very abstract concepts. Look where it landed. Just nailed it. The only happy person in the group got detected. And now, I don't know if you can really see from afar if there is a flag, but if you ponder, this is a very difficult task just for a computer vision model to see a flag, the tiny flag right at the top of the building. No problem. This is a very advanced model. It will locate this little like object over there. It detected and based on the concept, you can infer that this model has the whole context of the image. So flags are normally over buildings and they have the little, but it was like invisible even for a human. And the last one is, I want to locate teeth. So the only person with a big smile will be the one with the visible teeth. So another time it nailed it. It's very, oh, sorry. For this demo I didn't prepare it, but you indicate the model and it just shows the woman's teeth. What I did here is used the object detection part, and I indicated the model to look out for clouds. So it nails it. It just, based on the concept, it just knows those are clouds and gets it. This model, I want to clarify, this is not the huge model that OpenAI is using and uses like liters of water for query, like the popular saying says, this model can run into my machine. I didn't run it from a machine because I didn't want to ruin something, but this is a medium-sized model, and look at how powerful it is. Okay, so we are reached the end of the talk, and we have explored the whole path from pixels to concept to perception, and reaching chat models released like 2 weeks ago. I hope you enjoyed this talk, and now I am open to questions and comments, everything. Thank you for your attention.
Thank you, Rolo. There is a question in the chat box.
Could you read it for me, because
Yeah, sure.
I'm a little bit lost.
Yes, it says, can the model identify older people?
Yeah. I didn't test, but age detection was possible even for like 2016, 17 models. So I'm pretty I have the confidence that this state-of-the-art model will be able. I could try it live, but yeah, I don't want to ruin with a failed demo because everything works so far.
Okay, that is the question we have in the chat box. I don't know if anyone else has a question, you can raise your hand and just ask or type it up in the chat box. Well, they are saying thank you. It was very interesting.
Okay.
No questions apparently.
Okay, I think we are really punctual with the end of the talk. There are 2 minutes remaining, so
Okay. Great. So no more questions, just saying thank you and that it was a great talk.
okay.
Well, okay, Rolo. Thank you
Thank you,
very much
everybody.
for your time, and thank you everyone for joining us. And we recorded this talk, so if you want to rewatch it or if you couldn't join at the beginning, we can share with you the recording. So thank you very much. Thank you,
Bye
Rolo,
bye.
again. Bye bye.